Okay, so have you ever actually stopped to wonder what is going on under the hood of massive AI models like ChatGPT or Stable Diffusion? I mean, beyond the hype. Today, we're going to dive straight into the engine room of modern machine learning. In this explainer, we'll unpack the core mechanics of how neural networks actually learn. But more importantly, we're going to explore how a remarkably simple, almost too good to be true math trick completely solved a massive roadblock that honestly almost stalled the entire field of AI. So we do have a highly interconnected string of technical concepts to get through today. Here is our roadmap. We'll start with the mechanics of learning, then talk about descending the gradient, forward and backward passes, and finally, we'll spend a good chunk of time on our main focus, the infamous vanishing gradient problem, how a function called ReLU fixes it, and how this whole thing allows us to visualize some incredibly complex features.
All right, part one, the mechanics of learning, specifically looking at weights and biases. We're going to start at the absolute micro level here. To really understand the brain of an AI, you kind of have to think of a single artificial neuron as a tiny little mathematical processor. It takes in inputs from your data, and it assigns them weights to figure out just how important those features are. Now, if you look at standard visualizations, you'll see these weights are often colored blue for positive weights, meaning the network uses that output as a given, and orange for negative weights. After summing all those up, the neuron adds what's called a bias. This basically allows it to shift the output independently, giving the models some much-needed flexibility. Finally, it passes that whole result through an activation function to decide, hey, should I fire or not? Which brings us to section 2, descending the gradient, or finding the minimum. Because now that we know how a single neuron works, the really big question is, how do millions of them actually learn to be accurate together?
Well, the answer is gradient descent. I want you to imagine a hiker navigating this crazy mountainous landscape in the pitch black. Their only goal is to find the absolute lowest valley. In machine learning, this landscape is called the loss function, and that lowest valley, that represents the global minimum. It's this magical place where the model's prediction error is at its absolute lowest. So gradient descent basically tells our model to calculate the slope of the hill and just take iterative steps downwards, right in the direction of the steepest descent.
But as you can imagine, our hiker faces some pretty serious obstacles on the way down. They might get stuck in local minima. These are basically shallow valleys that trap the model way before it reaches the true bottom. Or they might hit plateaus, these big flat regions where the slope, the gradient, is literally zero, which just brings progress to an absolute crawl. This is exactly why the learning rate is so incredibly vital. Think of it as controlling the size of the hiker's steps. If the step is too small, learning takes forever. If it's too large, you might just completely overshoot the valley. It's this super delicate balance of precision and momentum. Okay, section 3, forward and backward passes. Let's look at the actual flow of learning. So we have our neurons, and we have an algorithm for finding the lowest error. Let's link it all together. First up is forward propagation. This is the network's very first attempt at making a guess based on the data. The data flows in one single direction, starting from the input layer, going right through the hidden layers where all those weights, biases, and activations do their math, all the way to the output layer. Once the model actually makes its guess, it performs an error calculation, essentially comparing its prediction to the actual reality of the data. And once that error is calculated, the network has to actually learn from it. Answer, backpropagation. This algorithm takes that error signal and sends it backward through the entire network. By using a calculus concept called the chain rule, it figures out exactly how much every single individual weight and bias contributed to the mistake, and it adjusts them layer by layer. This constant iterative loop of forward guesses and backward adjustments, that is the very heartbeat of machine learning. But wait, just think about that backward flow of information for a second. What happens if this absolutely crucial error signal just breaks down? Like, what if the message never even reaches the start of the network? And that brings us to section 4, the vanishing gradient problem. This was quite literally the fatal flaw of early AI. This is the core focus of our explainer today, the massive roadblock that stopped early neural networks from getting deeper. We call it the vanishing gradient problem. Honestly, you can think of it like a giant game of telephone. As the error signal moves backward through layer after layer of the network, the mathematical signal gets squashed. It gets weaker and weaker with every single step. So by the time it reaches the earliest layers of the network, the signal is so incredibly tiny that the early neurons basically hear nothing. The gradient just becomes zero, and those foundational layers, they completely stop learning. Early researchers were completely caught in a trap here. You absolutely have to use activation functions in your neurons. But if you use simple linear functions, sure, the signal survives, but your network essentially acts like a basic calculator. It can't learn complex patterns at all. So researchers tried using nonlinear functions like Sigmoid or Tanh. Now, these did allow for complex learning, but they physically squashed the numerical inputs into very narrow ranges, like between -1 and 1. When you start multiplying these tiny fractions backward during backpropagation through dozens of layers, the gradient practically vanishes to zero. So how do we get past this? Section 5. How ReLU fixes it, the magical artifact. Enter ReLU, which stands for Rectified Linear Unit. The coolest thing about this activation function is how brilliantly, elegantly simple it actually is. ReLU basically acts as a gatekeeper. If an input signal is negative, it just outputs 0, period. But if the input is positive, it outputs the exact raw input, completely unchanged. That's it. The function of x equals the maximum of 0 or x. It is a remarkably tiny piece of math, but it fundamentally solved one of AI's absolute biggest roadblocks. Because it doesn't squash positive numbers into these tiny little fractions, the error signal can actually flow backwards through a massive network without decaying. It's computationally incredibly cheap, and it is mathematically perfect for keeping the gradient alive. When you compare the old and the new, the upgrade is just undeniable. Sigmoid and Tanh suffer from vanishing gradients, and they're computationally expensive because calculating exponential curves takes time. ReLU, on the other hand, mitigates the vanishing gradient and runs lightning fast. Now, to be fair, we do have to watch out for something called dead neurons. Because ReLU outputs 0 for negative numbers, a neuron can sometimes get stuck outputting zeros and just permanently die during training. RIP to those neurons, for sure. But, honestly, even with that risk, ReLU is vastly superior for building deep networks. All right, Section 6, Visualizing Complex Features at the Macro Level. Let's look at what ReLU actually unlocks for us. Because ReLU keeps the gradient alive, we can stack layer upon layer upon layer. And what that depth allows the network to achieve is a true hierarchy of understanding. We can see this perfectly with the famous GoogleNet image model. In the earliest layers, the network is basically just detecting simple geometric edges. But as we move deeper, it combines those edges into textures and then patterns. By the time we hit the deepest layers, it's combining those patterns into actual parts and fully realized objects, like the face of a dog or the wheel of a car. Depth is exactly what creates this incredible layered comprehension. But here's the thing. To actually look inside these deep layers and see what the neurons are looking for, researchers have to use a technique called feature visualization by optimization. Essentially, they run the network in reverse. They tweak an image of random noise until a specific neuron fires wildly. Now, if researchers just run this without any rules, they get adversarial, high-frequency noise. It basically looks like a static illusion. So to fix this, they use something called transformation robustness. They are constantly jittering, rotating, and scaling the image during the process to suppress all that noise and force the network to show us a clean, clear visual of what it has actually learned. And it gets even more fascinating when you introduce diversity optimization. Researchers realize that a single deep neuron isn't always looking for just one strict thing. By applying a diversity term into the math, we can actually see the different facets a neuron responds to. So for instance, a single neuron might not just look for soccer balls. It might highly activate for soccer balls and tennis balls and golf balls alike. Sometimes it gets way weirder. A single neuron might respond to both fox faces and the bodies of cars. I know, it's completely absurd, but it proves that the way these deep models categorize the world does not always perfectly map to human logic. Which perfectly leads us to this quote from the researchers at Distill. By overcoming the vanishing gradient with surprisingly simple tools like ReLU, we built these phenomenally complex, deep models that can truly understand the world. But our next great frontier isn't just making them deeper, it's developing the visualization tools required to actually interpret them and to prove they're making decisions safely and logically. So, I want to leave you with this final, provocative thought. We solve the math to make networks incredibly deep. We are building the tools right now to look inside their layers. But as they become even more capable, running on billions or even trillions of parameters, will we always be able to untangle the math that makes them think? It is a massive question that sits at the very frontier of machine learning today. Thank you so much for joining me on this explainer, and keep questioning how the tech around you actually works.